15 plus kp equals 0. You divide by 4, the 4 cancels, and you get kp equals negative 15. So there's your stability criterion. So you need to make sure, so this is your root locus, and stability happens here. Kp has to be greater than negative 15. And if you did route Hurwitz, you would get that too. Kp is equal to 1 here in the center.
Yeah.
Kp is equal to 2 here.
Right.
You missed how to get the repeated root? Here's the quadratic formula. How do you get a repeated root? So what equals it? You don't want to do equal to 0 because you want a repeated root.
What's under the square root?
You want what's under the square root equals 0. Because then you get a repeated root of negative 8 over 2. If this term goes to 0, you get negative 4 twice. Right? So then you set 64 minus 4, 15 plus kp equal to 0. And then you solve and you get kp1. Okay? Why? You want to draw the root locus? How do you draw? This is an equation, right? This is like here. Let's go back to calculus or pre-calculus. You have x and you have y, right? And I have y1 equals negative 4 plus 1/2 square root of 64 minus 4, 15 plus x. And then I have y2 equals negative 4 minus 1/2 square root of 64 minus 4, 15 plus x. And then I say plot that. Does that work? If I plot that like that? No, because then you get an imaginary component. That's really annoying. So it doesn't exactly work like this. But this is kind of an analogy that you're trying to do here. You have kp as your independent variable, and you're trying to plot two lines, right? You've got this pole travels this way. That's y1 or y2, say, and then you have this pole travels this way. That's the second plot that you're trying to make. So if you are given a function, say y equals x squared, and you want to plot it, you plug in different values of x, and then you plot it on there. So here, we're plugging in different values of kp and then plotting it. That's what we're doing. So when kp is 0, we know it's negative 3 and negative 5, because we already factored it up here. Then when we find that kp is 1, we know it's a repeated root, so there's another line. We can connect the two dots. And then we tried kp is 2, and it's split, and then we just extrapolated from there. And then we wanted to see when it crossed this real axis, so we set the quadratic equal to 0, and we found that it crossed the axis here at negative 15. So basically what's going to happen is your roots are going to do this. Like you're going to have like kp negative 20, negative 18, negative 17, negative 16, negative 15, they're going to be here. Then you're going to get negative 14, 13, 12, 10, whatever. When you get to kp is 0, your poles are going to go here. And then you're going to start increasing kp. And as soon as you get kp1, they're going to meet. And then when you go greater than that, you're going to go up. And they're just going to go on to infinity. That's what the root locus looks like. So this is what I was looking for. And so we tried different values of kp, which is essentially what Ricky was saying. Just try different points and see where they lie on the graph. Cool? You have a question?
Yes, and maybe you can answer it quickly, but I guess I missed this. Is there a list of just what is got to be on a root locus plot?
Oh,
I mean,
where, yeah. How about poles at kp equals 0? Say, a direction of travel for kp greater than 0, and say direction basically, Kp greater than 0 is this, Kp less than 0 is this, and then poles at Kp 0 are here and here. I would say that would be sufficient.
But are those directions that always going to be given? I mean, they're always going to be the same?
No, there's not really a rule of thumb, unfortunately. Yeah. Because if we change the derivative gain, you're going to see that the whole thing is going to go out of nowhere, like it's going to be completely different.
So really, that's all we needed to do, was set the entire thing to 0
To find this point here,
which is what you asked for.
well, that was part of it, but I also asked for the root locus plot, so I did want this diagram.
Your KP inside the box here, KP greater than, is that a 15 or a 75?
Negative 15.
Okay.
Yeah, sorry. Alright, you ready for KD? Or we still have questions about this?
Less than, right? Can't be less than
You want Kp to be greater than negative 15 to ensure stability? Is that right? If
well,
Kp is greater than negative 15, you will still be stable.
right.
Yeah.
Well, I'm just thinking because your arrows are going towards unstable.
Oh, good point. How about that? So minus infinity is out here, and then they come in at negative 15, it crosses the real axis. At 1, they meet, and then greater than 1, they split. How about that?
I was tripping out because we're going from -5, -3, -15, but I see what's happening.
Yeah, the poles are -5, -3, the gain is -15, yeah.
So KP was negative 16, it's going to be unstable.
Yes. All right, do we want to try KD? Do you guys want me to give you guys a little bit more control on this one, see if you guys can do it? Kevin?
You found what the stability point by the quadratic motion here?
In this case, yes, I wanted, when Kp is 0, there's 2 real roots. So if you make Kp negative, the roots are still going to be real. So I can just set the real component equal to 0. And in this case, the whole thing was real, so I just set the whole thing equal to 0. Yeah. I think it'll still work out with KD, I'm just not entirely sure.
If there was an imaginary component, never mind.
Just where your graph goes like that, right?
Well, I mean, sometimes your graph will curve. That's why I was asking him, how does he know it doesn't curve? And you know it doesn't curve because Kp only affects this quadratic.
Yeah, it does curve.
Yeah, it's stuck at what, 4?
Because see, KD affects the real part and the imaginary part, doesn't it?
Right.
Because it affects the b term, right? So if you want to, let's we do plot I, and we have KD varies, Kp is 0. I get s squared plus 8 plus KD s plus 15. And so my quadratic formula is -8 plus KD over 2 plus or minus square root 8 plus KD squared minus 4, what's 4 times 15?
60.
Is it 60? See, these are my poles with KD. So this one's a little bit more complicated, right? Because if I change KD, I change the real and the imaginary component. So we're going to have to try a couple points to get this plot. Okay, so if KD is 0, where are my poles? -3, -5. So -5 here, -3 here. All right, can I get my poles to meet? Can I get this guy to go to 0? Is that possible? It's not?
Wait, yes.
How do I do that?
You said the square root is 0.
Okay, yeah, so I get 8 plus KD squared minus 60.
Bring the 60 over.
Bring the 60 over, square root of 60, which is something. square root of 60 minus 8. So when KD is equal to square root of 60 minus 8,
You get that real part.
I just get the real part. So when KD is equal to square root of 60 minus 8, and by the way, this is negative, isn't it? Because square root of 64 is 8, square root of 60 is less than 8, right? So this is a negative number. So when KD is equal to this negative number, I have repeated roots. What are they? What are my repeated roots when that happens?
-4.
Not quite, right? Negative 8 plus
0.
square root of 60 minus 8 all over 2. 8's cancel.
Square root of 60 over 2.
So that's like what?
There's a negative sign.
Oh, there's a negative sign. So what is that thereabouts?
3.87.
Okay. I was going to say it's about -4, right? It's close enough. It's like 3.8. So I'm going to get like here-ish. That's when they meet. But that's actually a negative number, right? So that means that my streamlines actually go this way. Because this is KD negative, this is KD 0. Does that make sense? No? Okay. What is KD equal to when my poles are here?
0.
KD is 0.
Yeah.
Okay? What is KD equal to when my poles are there?
-60 minus 8.
Negative 60, square root of 60 minus 8. Right? And what is square root of 60 minus 8? What's square root of 60? Say 7.6-ish? Minus 8. So it's negative 0.4-ish. Okay? So when KD is equal to negative 0.4, my poles are in the center. And so that means if I increase KD, I go this way. Okay, so now I have my two, go ahead, Moss.
Which way you said KD was going to go?
They're going to go this way, right? Because KD is negative, and then as I increase KD, right? KD, negative 0.4 is less than 0, right? So they're going to go this way. So now I have two different things, right? What happens if I make KD positive, and what happens if I make KD less than negative 0.4?
So they're not going towards.
They're not. They're backwards. I have a completely different.
Negative?
I have a completely different quadratic formula here now.
They like curve around it?
I don't know. We'll find out. So we have two different points to try. Okay. We need to try KD greater than 0. That's a question mark. And we need KD less than negative 0.4. So what points do you want to try?
8.
Let's try 8. 8 is greater than 0, right? Let's try KD 8. Okay, KD equals 8. I'm going to plug it into here. Okay, 8 who said 8? Why did you say 8?
Because I was trying to cancel out the 8 and the real one, but I didn't see negative.
Yeah, so negative 8.
Negative 8.
When you, yeah, we'll just try, let's try a different one. When we get to the negative, tell me negative 8, okay, just for kicks. All right. So somebody else, give me a number bigger than 0.
1.
1. There we go. Let's do that. Okay? So I'm going to get negative 9 over 2 plus or minus square root of 8 plus 1 is 9. 9 squared is 81 minus 60 over 2. So what is 81 minus 60? 21. Square root of 21 is 4.5-ish. So I get negative 9 plus or minus 4.5-ish over 2. So what is that? I'm going to get negative 13.5 or what? 2.25. Okay, so I'm going to get negative 13.5 or 2.25. Okay? So if I make KD bigger than 0, I'm going to keep going this way. right? Am I ever going to cross this axis though?
If you become unstable.
It could become unstable. What would I have to do to figure that out?
Quadratic equal to 0.
Set the quadratic equal to 0. Should we try that and see if that's even possible?
What is negative 9 plus or minus? What are those roots going to
I plugged in 1 into here.
Yes. Like the values?
Oh,
Can't really see
negative 13.5 and negative, oh, you said 2.5. My bad. Is that right?
Negative 3.5.
Oh, because you divide by 2, so it is 2.25. Yeah. Square root of 60 minus 8. I ished it. I don't actually know if that's right. 7.6 minus 8. Ish. Right? 7 squared is 49. 8 squared is 64. Square root of 60 is 7.6 in my world.
Can you leave that on the board?
Yeah, I'll leave it there.
We got to make sure.
Should we draw this bigger?
The negative 13.5 would be 6.75.
Oh, should it?
Yeah.
It should be 13.5 divided by 2?
Yeah.
Okay, let's draw this bigger. I've got negative 5, negative 3, that's KD 0. Here is KD negative, so my poles do this. If I make KP 1, or KD 1, I go this way, and I get negative 6.75, negative 2.25. And I want to determine, is it possible to cross this imaginary axis? Okay? Well, let's see. Here's the interesting thing. If I make KD 100, right? I do 100 plus 8, which is 108. 108 squared is something. Then I subtract off 60, right? And then I square root that. Is that number bigger or smaller than this? Smaller. So I subtracted off 60. See, if this 60 was gone, right? Say that 60 wasn't there, and I square rooted this, I would get 8 plus KD squared square root. I would get negative 8 plus KD. 8 plus KD, that would be 0. But I have this minus 60. So this number is always going to be smaller than this. Which means if KD goes to infinity, I'm still going to be stable.
Are you going to start curving the back make a circle or something?
Well, that's what happens if I make KD negative. Okay, does everybody see that? So even if you make KD infinity, you're never going to go unstable. But if you make KD negative, weird things can happen.
Is it going to start like curving up?
I don't know, man. I didn't actually work out this problem when I gave it to you. The people who got this answer right.
Are you?
Oh, I guess I don't have to. All right, we need to try another point. We need to try KD less than negative 0.4. What do you want to try?
Shoot mine.
He's texting.
Negative 8.
Negative 8. All right, let's try negative 8. All right, I'm going to try KD equals negative 8. So I'm going to get negative 8 plus negative 8 plus negative 8 over 2. So that's going to go to 0. Plus or minus square root. Let's see, 8 minus 8 squared minus 60 over 2. So I'm going to get plus or minus the square root of 60 over 2, which is really the square root of 60i over 2, which is, what do we say, 7.6i over 2, which is like, say what, 4? Let's just say 4i, because we can. What do you think? Plus or minus? So where are my poles? Imaginary axis, plus or minus 4.
And they're right at 0, so they're going to be on that.
Exactly. So if I wanted to draw a line, where do you think it's going to do? Is it going to do this, or is it going to, how's it going to do? It's going to curve out like, yeah, like this, right? So here's KD equals -8. There's your real locus. What happens if you make KD equal to -10?
Be a bigger circle.
It goes unstable. How do you know? Because it crosses at -8. So stability says KD must be greater than -8 for stability.
I thought it couldn't go unstable.
If you make KD infinity, it won't.
Are you gonna make it negative?
But you can make it minus infinity and it will. So there's your real locus, okay? So if you have like KD negative 10, you're going to be out here unstable, and you're going to cross the real axis. They're going to meet. What value do they meet at? What value of KD? Negative 0.4.
So we need to put all those values on it to get the credit?
No, you just draw it like this, you're done.
Well, I drew that.
You did?
Yeah.
Show it to me after class.
Okay.
That's good news for you, Crystal.
I wrote yes.
That's good news for you.
I think yes, it could be unstable or yes. Are we gonna tie all together or something?
No, this is it, man. This is PD control. You can do what you want. You can move the poles wherever you want. You can get the time response to be whatever you want. If you want to critically damp your system, what do you make KD? Negative 0.4. What if you don't have derivative gain and you have proportional gain and you want to critically damp your system? What do you do?
Make it 1.
Make KT 1. You see that? You are the designer, you're the control systems engineer. You can make real locus plots and you can make the poles do whatever you want. This is why I like control. I just like telling people what to do. But like I have like a moral issue. So like I just tell robots what to do. They don't have feelings. All right, folks. If you had an A in the class, 89.5 or higher, send me this completed solution in PDF. Just email it to me along with your final grade. That way I have something that keeps track of who's not taking the final. If that's not one of you, I will see you Tuesday at 8 a.m. Right? And remember, it's only going to be like 4 or 5 questions. It's going to be pretty much like last exam. So if you still don't know how to do this whole problem, I will be around today. I'll be around tomorrow. I'll be around on Monday. I'm available via email. One thing, I'm going to tell you guys a little secret. I'm not in my office a lot. You guys know this, right? I am in my lab a lot. Do you guys know where my lab is? Yeah. Shelby Hall 3318. So you go upstairs, go all the way to the end of the hall on the right. Okay, I'm usually in there like playing with robots. Just for this week and next week, if you want to track me down in my lab, I will help you out in there. Okay? Normally I try to go over there to get away from people, but I'm on your side, so I will try and make myself available. All right? So Friday, Monday, I won't be there on the weekend, obviously. And I'm not going to give you my address and my cell phone number. Anthony. Yeah, that's a good question. If you have an A and you just want to make the corrections on your test and send that, that's fine too. All right, guys, good luck studying. Heather, you have a question for the class?
I know this material was in there, but the other material that was for the test, only the material that was on the test for, or like.
Well, what was okay? Yeah, that's a good question. So, what else is going to be on the test? So, what was on the last test? Do you have it with you? Yeah, state space stuff, right? So, how do you? Yeah, converting transfer function to state space, converting back to it, the stability of state space, stability of this. Ralph Hurwitz. Can you send me an email with a draft of what you think will be on the test, and I'll edit it and send it back to the whole class? Nah. What else is on there? Laplace transforms. Can I not put gears? I'll put gears as a bonus.
Can you not put it?
I guess what I'm asking is, should I look at my previous test?
Yeah, and all your homework. Yeah, which is
It's not even fair, I just want to, do not know everything.
yeah. I mean, expect a problem like this. Now, I'm just going to tell you. I'm going to give you a problem just like this. Except instead of a quadcopter, I'm going to give you another machine, and it'll be pretty much identical.
It's in the book.
That's dangerous. There's a lot of stuff in the book.
That's just generalized.
Hey, James. Mom. Ben, what's up? No, front and back. You don't need any more.